So in the same way that we talked about combining sets of capacitors, now we're going to talk about combining sets of resistors. And they're going to fundamentally build off the same two principles. So we're going to basically build the rules that we come up with out of using our two Kirchhoff's laws. So first the loop rule, which says that the sum of all the potential changes as you go around a loop within a circuit must equal 0. And the junction rule, which says that the current entering a junction must equal the current leaving the junction. So we're going to use Kirchhoff's rules to build basically our rules for how to combine resistors. So let's start with resistors connected in series. So we said, of course, for any two elements connected in series, part of what that means is that the current traveling through one must travel through two. So again, if you think about applying the junction rule here, well, there is no junction as I come through my two resistors. So what this tells me is that the current through I1 has got to be the same as the current through I2, and that's also got to be the same as the current that I'm pulling out of the battery. So I here with no subscript, that's going to be the current that I'm pulling out of the battery, and that's got to be equal to, so whatever I pull out of the battery has got to go through I1 and has to go through I2. So my resistors in series have the same current. So now let's take that and use our loop rule. So again, as I go around my loop, so you'll notice that when we combine them, I end up with a single equivalent resistor. And so as I apply my loop rule, again, I'll go across the battery from negative terminal to positive terminal. That's going to be a potential increase. I'll go across my resistor in the direction the current's flowing. That's going to be a potential decrease. I'll go across resistor 2. That's also going to be a potential decrease. That gets me back to where I started. So I get the potential in my battery V minus the potential across resistor 1 minus the potential across resistor 2. That's got to be 0. Well, that's just got to be V equals V1 plus V2. And again, I know that for each of these, I can use Ohm's law to calculate what the voltage is in terms of the current and the resistance. So for the voltage of my battery, well, I know that the voltage of my battery, thinking about the loop rule over here, says that the voltage of my battery is the same as the voltage of my equivalent resistor. Again, the current I am pulling out of the battery has got to be the same current that goes across the equivalent resistor. So I can write the voltage of my battery, that's got to be equal to the current I pull out of the battery times the resistance of my equivalent resistor. And then V1 is just going to be equal to I1R1, V2 is going to be I2R2, but I1 and I2 are also equal to the current that I pull out of the battery. So you notice that the I's here are the same, which means they cancel, which means I'm left with a simple expression for how to calculate the equivalent resistance of two resistors in series. So of course there's a couple of things to keep in mind here. The first one is this is incredibly similar to the rules for combining capacitors in parallel. So when we switch from talking about resistors to talking about capacitors, the rule we use flips. The other thing that I want to keep in mind is that, again, when I'm combining resistors in series, that means I'm increasing the resistance because the equivalent resistance here is greater than each of the individual resistances. So that's connecting resistors in series. Now let's talk about connecting resistors in parallel. So again, any two elements connected in parallel, it's a situation where there's a junction, so the current that flows through element 1 and comes back into this junction over here to recombine can't be the same or is got to be different than the current that leaves this junction, splits, and goes through element 2 before recombining over here. So my current's going to split, it's going to recombine, some of it will go across element 1, some of it will go across element 2. So that means that I'm going to have some current through resistor 1, some current through resistor 2, and odds are good that these two currents are going to be different. They're clearly different than the current that's being pulled out of the battery. So for resistors in parallel, when I think about my loop rule, again, when I go around this loop here, well, what I see is I go across the battery with a potential increase, I go across resistor 1 for a potential decrease, and then I get back to where I started. So that tells me that the potential drop across resistor 1 has to be the same as the battery. When I use an outer loop, so now I'm going across my battery and then across only R2, come back to where I started. Again, that says that the voltage of R2 also has to be the same as the voltage of the battery. So it's easy to see from my loop rule that whichever loop I take, the loop across my two resistors, or the voltage across my two resistors, has to be the same as the voltage of the battery. So resistors in parallel have the same potential difference. They've got to have the same voltage. Well, now that I take that information and use it with my junction rule, so here's my junction, I know that I'm going to have the current that I pull out of the battery that's going to come into that junction, and then it's going to split. Some of it's going to go across resistor 1, some of it's going to go across resistor 2. And so my junction rule, and again, it doesn't matter whether I use the junction up here or the junction down here, they give me the same equation. What they tell me is that the current coming out of the battery is equal to the current going through I1 plus the current going through I2. Now the current coming out of the battery, if I think about my equivalent resistance circuit, well, now there's nowhere else for that current to go. It comes out of the battery and it goes across my equivalent resistor. So the current coming out of the battery has got to be the same as the current across the equivalent resistor. So that's why I've plugged in the current coming out of the battery. I've set that equal to the current through the equivalent resistor, and that's also got to equal the current going across the two individual resistors. Again, using Ohm's law, well, I can write current as voltage over resistance. So the current across my equivalent resistor has got to be the voltage across it over the equivalent resistance. The current through I1 has got to be V1 over R1. The current through I2 has got to be V2 over R2. But we said that all three of those voltages for the equivalent resistor, for I1, or for resistor 1, for resistor 2, all those voltages are equal to the voltage of the battery. And so again, you can see I got voltage terms that are going to cancel out. And again, I'm left with an expression that says 1 over the equivalent resistance is equal to 1 over the resistance of resistor 1 plus 1 over the resistance of resistor 2 when I'm connecting these resistors in parallel. Again, the most common mistake that students will make is they'll do this piece and forget to invert it. So if I just have two resistors, it's useful to go ahead and do the algebra and the inversion. And so I have an expression for the equivalent resistance as just R1 times R2, the product of their resistances, over R1 plus R2, the sum of their resistances. Again, in terms of thinking about these expressions, first thing I notice is this is basically the same as the rule for combining capacitors in series. So resistors in parallel combine in effectively the same way that capacitors combine within series in terms of calculating the equivalent resistance or the equivalent capacitance. The other thing to know is when I connect resistors in parallel, I'm decreasing the resistance because the equivalent resistance is going to be less than either of the resistances of my two individual resistors. So the equivalent resistance value is going to be less than either R1 or R2 the way that this is calculated. So when I combine resistors in parallel, I'm always decreasing the resistance. When I combine them in series, I'm always increasing the resistance. And so we'll use these rules to deal with our steady state circuits in class tomorrow.